go back to information dynamics. Today I'm going to talk about continuous type problems. So we have spent some time to talk about two-type problems and type problems, and today we're going to generalize everything to continuous types. I will first talk about problem setting in the first video, and then mathematical tools we need will be introduced in the second video. Then in the second, third, and fourth part, I will talk about how to reduce the problem and solve the problem. Finally, we will talk about the implications we may get from solving this problem. Eventually, you will see the whole point for doing these continuous type problems is to tell you or to show you that all those insights we obtain from those discrete type models are actually not so restricted. Okay, they will also apply to continuous type models. So let's refresh our memory from our two-type models. Suppose we have two types, theta 1 is less than theta 2. Okay. Here I'm talking about the monopoly pricing problem. If you have different problems, certainly your setting will be different. Okay? But this is our monopoly pricing problem. You have two types, so you need to design two contracts for them to select. One QT pair and another QT pair. So you have Q1, T1, Q2, T2 as your decision variable. Then you want to maximize your expected profit. Beta is the probability for you to see the first type. So beta times T1 minus CQ1 is the profit you may get from the first consumer. And then this is your second, your profit facing the second consumer. Okay. Then what's interesting is that you need to have four constraints. Okay? The first two are IC constraints. They are saying that as type 1, it will be better for you to tell the truth instead of pretending to be type 2. For type 2, it will be better for you to tell the truth instead of pretending you to be type 1. Okay? The key is that we design contracts to be incentive compatible, so that we can induce them to tell the truth. Also, we need IR constraints to make sure that they will participate. So you have constraint 1 and constraint 2, making sure that each of them, by telling the truth, can earn some money. Okay? That's the two-type problem. And then we spend a short time to talk about discrete type problems. So suppose we have n types, n may be 3, 4, 5, or 1,000. Okay? And we assume for theta, there is some kind of orders. Theta 1 is less than theta 2 and less than blah 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 and then theta n. Okay? In this case, we say we want to design n pairs of QT or n contracts for these n types of consumers to self-select. Okay? So then in that case, we hope for type I will choose Ti and Qi. So I will earn beta I times Ti minus CQi from type I consumers. And then this is my expected profit. Then for IC constraint, it's just this thing. For type I, saying that it is type I is better than pretending to be type J for all I for all J. Okay? And also, for type I, telling the truth can earn some money. In this case, we have IRIC constraints and we have this discrete type problem. So even though there are so many constraints in a discrete type problem, we can show that we can eliminate some constraints, and we only need the following things. First is about IR constraints. We know only for the lowest type, theta 1, we need the IR constraint. So all others can be removed, and we only care about the IR constraint for the lowest type. Okay? Only for type 1, we need to have this IR constraint. Also, for IC constraints, we only need those IC constraints that is preventing type I to pretend to be type I minus 1. Okay? This is saying that if you are type I, telling the truth is better than pretending to be your next lower type. Okay? Okay. We call this IR1, and we call this we call this set of constraints local downward IC constraints. Okay? Local means you only compare compare yourself with your neighbors, and downwards means from I to I minus 1. Okay? Yeah. Objectives can be the same. Yeah. So we have shown that this original problem can be reduced to this reduced problem. Yeah, according to our derivations. Okay? In this case, you don't need n square constraints, you only need n constraints in total. Okay, so now what's our continuous type problem? Oh, let's write it down. Now we do not assume we have a discrete set of types. We assume that okay, continuous type. We assume that the type theta is between the lower bound and the upper bound. We call the lower bound theta lower bound, and the upper bound theta upper bound. Okay? Within a range, consumers, their valuations spread over this range. Okay? So you may, for example, say a consumer's type is between 50 and 150. You know it's within this range, but you don't know what's it. Okay. So now the question is, how would you describe the distribution? Okay, like beta 1, beta 2. Now, because this is a continuous distribution, you need a PDF or a CDF. Right? From the principal's perspective, theta is random. So this random variable follows the PDF function small f or CDF function capital F. Okay, so this is the setting. So with that in mind, let's write down the problem. First is again the IC constraints. Okay, here I'm going to say that for each theta, if you tell the truth, okay, this is how you will earn when you tell the truth. Okay, the key difference from the original one to the new one is that here your decision variable will be Q of theta and T of theta. What does that mean? For each type, you need to offer a contract, right? And now you have infinitely many types, so you need to decide infinitely many contracts. At the end, you know you are actually determining functions. Okay? So your decision variables are exactly functions, one function and two functions. Okay? So for type theta, he is going to take Q theta and T theta. So this is the type theta's payoff when he sees this. Okay? This must be greater than or equal to this one. But theta does not change. He is still him. But now he may choose another contract by pretending to be theta upper bound, theta head. Okay? In that case, we need to make sure that lying is not better than telling the truth for all possible theta and the theta head. But similarly, telling the truth earns something. Okay? And finally, for our objective function, from the summation, now we need to jump to integration. We do an integration from the lower bound to the upper bound. For each type, I'm going to earn T theta minus CQ theta. Right? And then, what's the likelihood for me to see it? Is small f of theta. D theta. This is a continuous generalization from this summation. Yeah. So the problem here is that we have a continuous type. So our target or our mission for today's lecture is tell you how to solve this problem. Okay? You should be excited about that because this will be your first time in your life to solve a problem with infinitely many decision variables. Okay? We're going to tell you how may we solve it and implications. Thank you.